So today we will look at MOS capacitor. So here MOS stands for M for metal, O for oxide, and S for semiconductor. Okay, there are three types of material. These materials are classified according to the electrical characteristics. Basically, the conductivity of these materials are very different. Okay, metal has very high conductivity. Oxide has almost no conductivity. It's another way we can look at it is it's an insulator, and the semiconductor is having conductivity which is somewhere in between metal and oxide. Okay, so if I draw the structure, say this is my metal, and then I have an oxide, and then I have my substrate, which is basically made up of semiconductor. So depending upon the fabrication technology, either we take a p-type substrate and fabricate transistors upon it, or we will take a n-type substrate and fabricate upon it. So there are various different approaches for making the transistor. We will look at fabrication a little later. Maybe after I cover transistor and transistor based circuit, I will come into fabrication part. So we need to look at that also. So let's say we start with a p substrate. I hope all of you understand what is meant by p-type semiconductor, n-type semiconductor, etc. So, and then we have oxide. Oxide is basically, though we say oxide, it is basically silicon dioxide. Okay, so this is SiO2, and then we have a metal, okay, to which we connect terminal. So for MOS capacitor, it is a capacitor that is made out of metal, oxide, and semiconductor. So oxide region acts as insulator. In general, we know that capacitor is like two plates. It has two plates separated by a insulator. So here only difference is that one side it is semiconductor and other side it is metal. So something which is highly conducting. Okay, so I just to distinguish it from the substrate, I am just putting some different shade here. Okay, so this is metal. So it is very common that instead of metal we use what is called as polysilicon. Okay, so polysilicon is basically not a crystalline silicon. Okay, so silicon exists in various ways. One is called crystalline silicon, which is what the substrate is made of, and then we dope the crystalline silicon to get p-type silicon. But so let me just write that explicitly here. So silicon could be either in pure crystalline form, or it could be what is called as amorphous. Amorphous means there is no periodicity throughout the material. It's like some powdered kind of format. Okay, the structure inside is not regular, and somewhere in between you have what is called as polycrystalline. So it's something in between. So So if you take a block of polycrystalline material, so it will have various region which is crystalline, something like this. So there is periodicity here, and then the neighboring region will have a different orientation, but within a region things are periodic. So different angles they are going to be something like this. So this is what we call as polycrystalline structure, multiple crystalline region, and each region may be of the order of say a few nanometer. So 10 to 100 nanometer may be the size of this one region, may be of the order of 10 nanometer. Okay. And they are very conductive compared to pure crystalline silicon, which has like entire thing like one regular structure, fully periodic. Okay, so compared to pure crystalline, this polycrystalline structure is very conductive, whereas in amorphous we don't have any regular arrangement at all. Okay, so this terminal, the highly conductive terminal, we call it as gate, and this one we can call it as body, sometimes it is called as bulk. Okay, so for MOS capacitor we have only two terminal. It's a two terminal device, just like any capacitor. This is also a two terminal device. Now, to fully understand what is going on, we need to have some idea of band structure. So band structure, I don't know whether you are familiar with band structure, PN junction band structure, any semiconductor material or devices that you come up with can be well explained with the help of band structure. So if you have a device course, probably you might have learned it. So here, to understand the operation of a MOS capacitor, we should go to its band structure. So here there are three different materials if you look at. So there is a polysilicon or metal material, and then you have silicon dioxide, which is a different material, and crystalline doped semiconductor, which is the P substrate, that is also a different material, and each of this will have different characteristics. And nowadays it is also common to use the insulator as different material other than silicon dioxide. Originally we always use silicon dioxide, but if you look at the current technology, they take material with large relative permittivity. Okay, so that has some advantage, as it would help us to reduce the width or the thickness of the oxide or thickness of the insulator. Okay, for silicon dioxide, epsilon r is around 3.9. okay, but there are materials with say relative permittivity which is of about 10 are available. So the larger the relative permittivity, the better it is. Okay, so these are all some material constant. Okay, so let us look at the band structure of these individual material first. So first of all, let us take a metal. Metal band diagram is quite easy to see, and all band structure have a common reference level, and that reference level is usually called vacuum level. Probably when you studied photoelectric effect and all, you might have come across what is called as work function and vacuum level, etc. So that is going to be the energy at which the electron becomes, can become free from the material. Okay, so So this is so if I talk about the metal, then apart from the vacuum level, so this is my vacuum level. Any electron with energy above the vacuum level energy, it becomes free from the material. Okay. So apart from that, we will have another very important level for metal, which is denoted by an energy. So what I am drawing is all electron energy. Okay, so this is EFM. What does EFM stands for? EFM stands for the Fermi. F stands for Fermi energy of the metal. Okay, M stands for metal. So as you can see, EFM is the Fermi energy level of metal. Fermi energy level of metal. Now it is common to draw conduction band and valence band, edges when you draw the band structure of semiconducting material, but when you draw it for metals, the edge of valence band and conduction band is not important, because metals are material in which valence band and conduction band overlaps. Okay, so therefore we will not need to draw EV and EC. EV means the top of the valence band and EC means the bottom of the conduction bands. So here all these energies are continuously available for electron to go into. There is no energy gap here. Okay, so that's why I'm not or usually it is not drawn for metals. So this difference in energy, is denoted by Q phi m. Okay, Q phi m, and so phi m is something like the work function. Okay, so so let me write that. So if you express it in electron volt, the unit of energy we usually take here as electron volt. So when you multiply some potential, so phi is basically a potential, and if you want it in energy, then you multiply with the Q. Q is like minus 1.6 into 10 raised to minus 90. Okay, so Q phi m is called the work function. Okay, so in other words, EFM denotes the energy level up to which electrons are filled in a metal. So all this region, there are electrons. That means all the energy up to EFM, electrons are occupying in a metal. Okay, above EFM, it is all empty, but spaces are available, but they are not occupied because there is a finite number of electrons, though they are large in number inside the metal. So they will try to fill up from the ground state, and as it fills up at some point of level, everything is filled, and so there is no more electron to fill up the energy levels above it. So there is a continually spaced energy levels which we call as band available, but only up to EFM it is getting filled. Okay, and if you want to liberate an electron, then the topmost energy that is occupied is basically correspond to EFM. So you need to apply a work which is Q into phi m in order to make it go into the vacuum. That means to liberate the electron. So work function is the amount of energy that you need to give to an electron in order to make that electron go out of the material. Okay, so that's basically describe the band structure of the metal. So that's quite simple. Now if we go into the oxide region, now oxide and semiconductor, probably you are already familiar. So oxide has large energy gap. So if I may draw this, the large energy gap, suppose it is like this. So this distance is basically going from metal and then oxide and then semiconductor. So so what I have earlier drawn, the structure I have drawn it vertically, but the energy band diagram I am drawing by keeping the device laterally. Okay, so right now I am not connecting it, so I don't want an overlap here, so I will keep it disconnected. I am drawing it separately. Okay, so for some region there is the oxide. Now what are these two levels that I am drawing? So maybe I can remove this. This vertical line is not necessary. Okay, there are two levels that I have drawn. So the bottom level I call it as EV. Okay, this is the top of the valence band but of oxide. Okay, so oxide I will denote by O, and this is conduction band, the bottom of the conduction band of oxide. So in between there is a large energy gap which which is like forbidden gap, and electron cannot occupy that energy, okay, because there are no states available there. But there is a band here which we call as valence band, and there is a band here which is called as the conduction band. And then you have again this vacuum level is common of all the material. This is something like a reference. Okay, right now I have not connected these materials, so we are looking at them separately. Valence band, it is completely filled, but conduction band, it is completely empty, because the electrons are not able to go from the valence band to the conduction band at room temperature because of the large energy gap, and this gap may be something like 5 electron volt or something like that. Okay, so the probability of electron going into the conduction band from valence band depends upon this energy gap. If the energy gap is very big, they cannot go, because the average energy of electron is due to the temperature. At room temperature, this thermal energy is of the order of 26 millivolt. If I put it in electron volt, it will be like 0.026 electron volt. So 0.026 is much smaller. That average energy of electron in the conduction band will be valence band will be much smaller. With thermal energy, it is not able to cross something like 5 electron volt barrier. So it's like many orders of magnitude larger. So that is why the insulators are not good conductors, because there is no vacancy available in valence band. There are no holes here, and as well as there are no free electrons in the conduction band because of the large energy gap. So, and you can also define what is called as electron affinity, which is defined by this quantity Q chi SI O2. Okay, so this is basically something like the work function. We want to specify electron affinity is the energy required to raise the electron from the bottom of the conduction band, that is here. Suppose if there is an electron how much energy you need to raise it so that it will reach the vacuum level. Okay, so but there is a very less chance of having electron here, but still we can define this term in that way. Okay, so let me write that also here. So Q chi SiO2. So this is called electron affinity. Okay, what is electron affinity? It is the energy required to raise the electron which is at the bottom of the conduction band to go into the vacuum level. Okay, so that's about the oxide region. Okay, so we saw metal, we saw oxide. Now we come to semiconductor. Okay, now in semiconductors there are a lot of things. So again there is going to be conduction band and valence band, but they are not very far away. So let me just draw it. So I'm going to so again I don't want to connect them. I'm drawing again separately. So this is my EV, and then somewhere here I have my EC, but you can see that in comparison with oxide the forbidden gap is much lesser. So for silicon it is of the order of 1 electron volt. For germanium it is even smaller. So depending upon what is the material with which you or what semiconductor it is, what material it is made of, this energy gap will vary. Okay, it's entirely a material property. Okay, so then there are other important levels. One is called somewhere at the middle of EV and EC we will denote it as EI. Okay, so EI stands for intrinsic level. Okay, I will come into the significance of intrinsic level, and therefore you can say that this difference from EC to EI, it is basically half of the energy gap. Okay, same thing goes toward bottom also. Okay, so then what else we have? We have Fermi level. Okay, so Fermi level we have to draw depending upon what is the type of semiconductor. So if we are talking about p-type semiconductor, Fermi level okay, so Fermi level for p-type semiconductor will be closer to the valence band. Fermi level is not an physically existing energy level, but it is actually a level. It's theoretically that we put that level there in order to explain its conduction properties. So it is between, yeah, if it is between, if Fermi level is between it is between EI and EV, then we have p-type semiconductor. Okay, so this is my EFS, just like EFM I wrote here, this is EFS. Okay, so and then we have, similar to earlier, I have the electron affinity defined for this semiconductor, which is Q into chi S. Okay, so you need to pay much closer attention to what I am going to say from here onwards, because there are certain concepts, if you don't pay very close attention, you will find it difficult to understand. Okay, but I will go slowly Okay, so the Q into chi s, just like so this is electron affinity of SiO2. Similarly, Q into chi s is the electron affinity of semiconductor. Okay, and EI I already told you, it is intrinsic level. So that is EI is also not a physical level. EFS is also not a actual energy level where electron can go in. They are theoretical concepts which will be very useful to explain certain things. Okay, whereas EC is actually a physical energy where you can put electrons. Okay, so there is a band here which is called the conduction band, and there is a band here which we call as the valence band. So this is the valence band, and this is the conduction band. So electrons can be present in conduction band, it can be present in valence band. So at 0 degree Kelvin, all electrons in a semiconductor will be inside the valence band, nothing will be there in conduction band. But as you raise temperature, some of the electron will find enough energy, thermal energy, and they will occupy some of the states in the conduction band. Okay, and p-type and n-type is another thing. So if it is a p-type material, it will create some additional levels in the forbidden gap, because we are adding certain impurities, and therefore to those impurity levels, electron from the valence band can go very easily, because they will be very near to the top of the valence band, which I denoted as EC. Okay, so if you are talking about intrinsic semiconductor where we do not do any doping, the Fermi level is basically coinciding with the intrinsic level. Okay, so that means the probability of occupying electrons or finding electron in that energy level is half. Though there are no states available, we can still talk about the probability of occupying. So intrinsic level is that level at which the probability becomes half for an intrinsic semiconductor which is not doped. Whereas for doped semiconductor, the Fermi level will either shift from EI to above or from EI to below. If it is a p-type semiconductor, the Fermi level will shift downward. Okay, as you dope, you are basically shifting the Fermi level toward EV. But if you are doping with n-type impurity, you are shifting it upward toward EC. So that is what doping does. You are changing the location of finding the Fermi level either upward or downward. Okay, so n-type, for n-type EF is generally EFS. Okay, that will be greater than EI. It will go upward. For p-type, EFS will be below EI. Okay, it will come. So what I have drawn is for a p-type semiconductor. Okay, so here there is metal, then I have oxide, and then I have p-type semiconductor, and they are not joined at all. They are taken separately. Okay, so I am drawing a case where each of the material are separated. Now the difference between the difference from here to here, that is from EI to EFS. Okay, so that is denoted by Q phi b. So what is Q phi b? So Q phi b, so that is basically the you can say the shift of the Fermi level from the intrinsic level. Okay, shift of Fermi level from EI. EI is the Fermi level for intrinsic semiconductor. So this 5B is a consequence of doping. So if you have not doped the semiconductor, then your Fermi level is going to be at EI. But because of the doping, it gets shifted downward or upward. If you are doping with the p-type impurity, it will shift downward. If you are doping with n-type impurity, it will shift upward. Okay. Now another very important thing is that so now when we join these three material, what is going to happen? Okay, so that is where some of these concepts of semiconductor, Fermi level, and each of the location of the bands are going to play a role. Okay, so we will go step by step. The first case that I am going to consider is that the sum of let me define one more thing here. So that is basically this from here to here. This one I will call, just like here I have called it as Q phi m, I will call it as Q phi s. Okay, so if Q phi m is equal to, or phi m is equal to phi s, okay, what is phi m? Phi m is the work function. So you can consider Q phi s also as the work function of the semiconductor. If the work function of the semiconductor is the same, and they need not be same, as you can see that it depends on the doping. Okay, the Q phi b will depend upon the doping. If it was n type, it may go upward. If it is p type, it may come downward. So there is no need, even if you take polysilicon and silicon, it need not be equal. And oftentimes we also take different material for gate. That is, you can take aluminium, we can take copper. These metals are also common to be employed for gate material. So there is no necessity that phi m is equal to phi s. But if phi m is equal to phi s, then drawing the band diagram is quite easy. You just need to connect all the three. Okay, so otherwise there is a lot of physics that will go into it. Okay, so let me just take the simplest case. So this is going to be case 1, which is a very simple case. And what is a simple case? What I am saying is phi m is equal to, that is the work function of the, so I did not write that. So here this is the work function of metal. Similarly, I can write phi s as the work function of semiconductor. So if phi m is equal to phi s, okay, so then if we join these three different material, the band structure drawing is quite easy. So let me do that. So again I am drawing the vacuum level. That is something like a reference, and then I have my metal region. Then the way you need to draw is that you have to make sure that the Fermi level on both sides, that is this side it is EFS, and on the other side it is, sorry, here it is EFM and here it is EFS. They should align each other. In this case there is no confusion because we are taking this from vacuum level. This is our Q phi m, and here this is my maybe I should use a different color. Okay, so this is my Q phi m, and then I have my Q phi s. Okay, so they are same. That's a condition or the case that we are considering. So definitely without any confusion you can draw them like this. and in between we are drawing the this one. This is basically our insulator conduction band and valence band. Since there is a material change, I'm going to or so let me okay, so here so EFS, this is p-type semiconductor, so my EI will be above this. Okay, my EI is going to be above this. This is my EI, and from EI, if I go some distance above, this is my EC. So this is my EC, and here my valence band. So this is my EG by 2. So if I take one more EG by 2 downward, I will reach the conduction band. So EI is middle of EC and EC and EV. So this is my EV. Okay, so it will come like this. Okay, so this is how it is going to look like. So this is my conduction band edge, and this is my valence band edge, and then there's a jump from semiconductor to oxide when I go. So there is going to be a jump. So this is my Q chi SiO2, and this is my Q chi S. Okay, so the important thing is that okay, just let me I can just for simplicity I'll just draw like this. Okay, and now if you look at these 2 points, they are aligning each other, and the vacuum level is flat, and all the energy level, they are going to be flat. EV is flat line throughout the semiconductor from this end to the other end, and EC is also flat. Okay, this need not be the case if phi m is not equal to phi s. So that is what I am next coming into. But here, as I told, this is a easier case to draw because there is no bending of band. When you join them, there is no bending of band. All the bands are flat even after joining. Before joining it was anyhow flat, but after joining also it is going to remain flat. One more energy level I think I should show here, that is this difference. This is Q into phi b. Okay, so that's the case for phi m equal to phi s. So now we are going to consider a case where which is a different case. Now let's consider 2 cases. So we are only looking at joining of 3 different semiconductor material and then drawing their corresponding band structure together. Okay, so initially we drew them separate, and then I said that if the condition is satisfied, phi m equal to phi s, then you can just simply connect them from 2 sides. But now what we are going to do is we are going to take a case where say for example phi m is let's take phi m is less than so case 2 case 2. So here phi m is not equal to phi s. So it can be either greater or smaller. So let me take phi m less than. Okay, so I am taking a special case. So once you understand how we can draw when phi m is less than phi s, you can find out how it should be for phi m greater than phi s. Okay, so but this is something that you need to follow very closely. Okay, so how do I start? I start with again the vacuum level. Okay, and then for metal there are not much things to be bothered about. So we have our phi m here. So whatever is the value of that phi m, accordingly you take okay, suppose this is our q phi m. Okay, so what we can do is we can draw here what is called as EFM. So far everything was same. Okay, now what is going to happen is so this was the vacuum level. Now when I draw this Fermi level, since there is an insulator is in between, there cannot be any current from one side to the other. Okay, as long as the insulator is in between, there cannot be any current. And if there is no current, the device physics or the theory says that I cannot go into that theory why it has to be like that, but you have to take it, because otherwise I will just keep on teaching you only the device. We can't, somewhere we have to limit. Okay, so if there is no current, so this is the thing you need to know, that this Fermi level has to be continuous throughout the material. Okay, so that means your semiconductor Fermi level, which we earlier denoted as EFS, should align with the EFM. Okay, so you may think, how is that possible, because our phi s should be larger. Okay, now the answer to that is that the vacuum level is going to change. Okay, the vacuum level is going to change. So far away from the oxide, if I draw the vacuum level, it will be changed by some amount. Okay, such that this is, so this is still my vacuum level. Okay, so I can write here vacuum level. So vacuum level in the semiconductor is up, because this has to be Q into phi s. Okay, so this is the condition I told you. Phi s is going to be greater than phi m, and next thing I told you is that the Fermi level has to be continuous. So if Fermi level is continuous and phi s is greater than phi m, then the only thing that can happen is that vacuum level has to be at a higher energy in the semiconductor side compared to the, so that means there is going to be some sort of band bending, and in this present case the bending is going to be from, it is going to increase in height from left to right. That means from metal to semiconductor it is going to increase. So how do we draw in the case of metal? Now the answer to that is this difference. Okay, so this difference is not entirely put upon the insulator in between. It is partly dropped across insulator and partly dropped across this side of the semiconductor, which is nearer to the insulator or the oxide. So what is going to happen is that so if I may draw this more properly, or let me okay, so here there is going to be a bending. Okay, you can see that the vacuum is bending, and then after that there is a smooth bending. like this. Okay, initially there is a linear bending, so that is basically the oxide region. If we could connect with the previous diagram, okay, so that is okay. So let me draw the conduction band like before. So I have extended, I don't need to extend it. So this is my conduction band, and somewhere here is my valence band. So this is where you need to be very careful, otherwise you can run into confusion. Okay, so the step by step you need to draw this to get it correct. So this is going to be continuous. Okay, all right, so the Fermi level should be continuous as long as there is no current. Why do I say there is no current? That's because of the insulator layer is between the metal and semiconductor, so it cannot pass any current through it. Okay, so this is my valence band. Now what about the situation of other bands in the semiconductor? So away from the oxide layer you can draw things very easily, but as you get nearer to the oxide layer you have to be careful how do you draw it. Okay, so away from the interface, say this is my EI, and then I have EC. Okay, now you see that the band bending is not over here, so there is a bending within the oxide. Now I will call this as this drop across oxide, which is same as here also. These all are same drop. This is the amount of energy difference from one end to the other end of the oxide layer. So this I will call it as Q into psi ox. Okay, and the remaining bend, okay, so from here to here, so there is a bending here also, that is within the semiconductor. So this one I will call as Q into psi s. Now this bending is going to be common for all the EC, EI and EV. Okay, so that is how you have to look at. So whatever is the bend here, that is going to be common. So that means it is going to bend like this. Okay, and this is also going to bend like this. And similarly this also is going to bend like this. Everything is going to bend. How much it is going to bend? This difference, again it is going to be this is going to be Q phi s. Okay, all the bands are going to bend when it reaches. So what is the physical significance of this? I will come into it maybe in the next tomorrow's class, but so this is what you have to keep in mind. So this is basically Q into psi s. So every band is going to bend by Q into psi s near to the oxide. Okay, I can okay, but the Fermi level has to be flat. It has to be flat throughout, across the material. It has to be flat. So that is like our reference, and with respect to that, every other bands have bended. Okay, but away from the oxide interface, oxide semiconductor interface, there is no bending. They are still flat. Okay, there is no influence affected at far away from the interface, but near to that there is a bending, and also across the oxide layer there is going to be a bending, and we are going to calculate what is going to be this psi ox and psi s. So if you don't understand how to draw this, it is going to be very difficult. Maybe if you have a class, I will stop here. We will continue in the next class, but today what we have done is basically to consider the case of phi m equal to phi s and phi m not equal to phi s. Now we have taken specially phi m less than phi s, but what would happen if phi m is greater than phi s? So that is something that you should be able to draw. So I would give that as a homework. You try what happens if phi m is greater than phi s in order to satisfy whatever I said. That means Fermi level has to be continuous, and then phi m on this side is going to be larger compared to phi s on this side. So there will be drop across oxide as well as at the interface region. Okay, so that you try to draw. We will stop here.